Okay, so this is a summary of the scalings from step 3, and we're going to be using that now. So I want you to imagine that the action is just the usual free field action. So it's an integral dx of 1/2 d mu phi d mu phi. If you go ahead and you do the 3 steps 1, 2, and 3, so do 1, then 2, and then 3, you'll find that S is equal to the effective action. So this, that's just a fact, okay? So S doesn't change. Okay, good. So I want you to bear that in mind. Now, in general, I'll give you some action. What you'll then do is you'll complete those 3 steps. So first you'll separate out a shell of momentum modes, then you'll integrate over those momentum modes, and then finally you'll do the rescaling that's needed. And then you'll start again with step number 1, step number 2, step number 3. By continually repeating these 3 steps, in general, the couplings of your action will change. The sizes of the different terms in your action will change, and you'll move to a different point in the space of all possible theories, okay? That change in the action, the way you move around in the space of all possible theories, it's a smooth change. You will trace out a trajectory, and this is called a renormalization group trajectory. And moving along that trajectory is called a renormalization group flow. We say that the free field theory is a fixed point of the RG flow, okay? And it's got a special name. It's called the free field fixed point. And I'll often want to refer to it. I'm going to call this the FFFP, the free field fixed point, okay? One way, if you're working in perturbation theory, so if you're working in perturbation theory, that means you are working at weak coupling. What this means is, another way to say it is, you are close to the free field fixed point, okay? That's what it means to be at weak coupling, and that's what it means to be close to the free field fixed point. And this is where perturbation theory is valid. So working in perturbation, let me put here theory. That's the same as saying you're at weak coupling. That's the same as saying you're close to the free field fixed point. If you are close to the free field fixed point, then close to the free field fixed point, remember that step number 2 doesn't produce a big change at weak coupling. So close to the free field fixed point, we will simply ignore the effects of step 2, okay? And this is valid if we're at weak coupling. We'll ignore the effects of step 2. And then the biggest change in the couplings, in the action, biggest change in the couplings is due to step 3. And that's these rules that we've got sitting above here. So if we're very close to the free field fixed point, we can ignore step number 2. Sometimes we have to take into account, and we'll discuss when we do. But most of the time, we can just ignore step 2, and we'll get a pretty good description just by using the scalings that we discovered inside step 3. So let me give you an example. So imagine there is a term in the action of the form. So it's got a coupling. I'm going to call it lambda, capital M, capital N. And what capital M and capital N count, there's a total of M derivatives and N fields. Now, I've been very schematic here. So let me give you a detailed example with a specific M and N. So we could have the integral d dx. We might have d mu1 phi, d mu2 phi. Perhaps we'd have a d mu3, d mu4 phi. And then we might have a d mu1, d mu2, d mu3, d mu4 phi, and say a phi to the 6th. In this term, if you count, there's a total of 8 derivatives, so m is equal to 8, and there's a total of 10 fields, so n is equal to 10. But you can see the indices are properly contracted, so all of the mu's are contracted, and that means you preserve the SO4 symmetry that you would have in Euclidean space. That's the analog of the Lorentz symmetry in Minkowski. So that's an example of what the term would look like. I'm just going to keep schematically referring to it the way that I've done it above this boxed equation. Then what we might want to know is, let's say that we start to do an RG flow. So we do steps 1, 2, and 3, and then repeat 1, 2, and 3, and then repeat 1, 2, and 3. How will the coupling of this term behave? And we're going to answer this in the simpler setting where we're very close to the free field fixed point, so we can simply ignore the effects of step number 2. So we only need to take into account how it would transform according to the changes implied by step number 3. And there are the scaling laws. Actually, we're going to be using them. So let me just recapture them so that you can actually see them, well, and also so that I can see them while we're actually working this out. Duplicate, good. So this is where all of the change is going to come from. Okay, so let's imagine we've done steps 1, 2, and 3. Then what will we get after having done these steps? Well, we will have the lambda mn sitting up front. So good. So there's lambda mn sitting up front. And then what would we have? This will be times by. So we've got an integral d dx. I want to change it to an integral d dx prime. So I'd calculate the Jacobian for this transformation, knowing how x and x prime are related. That will give me, let me just so lambda mn, I will have an integral d dx prime. There's a Jacobian sitting up front, and that Jacobian is given by 1 minus b to the power of minus d. Okay, so very straightforward to calculate the Jacobian. You've done that a few times. Then we need to transform the derivative. You can check that each derivative picks up a factor of 1 minus b. So this will be raised to the power of m, and we'll have d primed m. And then we need to put in our field. And each of our fields picks up a factor 1 minus b. Now, here it would be easier to know what is phi in terms of phi prime. You just reverse the sign of the power. So we would get n, and then let's write it as d minus 2 over 2 times by phi prime. Okay, so I'm just using the scaling laws to work out how this would transform. And now let me pull out all of the scaling laws up front. So we've got a lambda mn, we've got a 1 minus b, we've got minus d, we've got plus m, and plus n, d minus 2 over 2, and then we've got an integral d dx prime. Sorry, let me remove that. Good. Then we have got d primed to the m, phi prime to the n. Good. So that coefficient that is sitting up front, that is what we would mean by the coupling after we did these 3 steps. So this is the coupling that we get after repeating, or after doing 1, 2, and 3. And then we would repeat it again, okay? All right. Now, it is very easy, especially for me, to make a mistake. So let's actually do an example. Let's study the free action. So the free action looks like this. It's an integral d dx. And we would have a 1/2. We would have a d mu phi, d mu phi. So in the language above, this would be a lambda 2 term. So lambda 2 is actually a half, but it would be a lambda 2 term. Why 2? We've got 2 derivatives and 2 fields. So let's work out what lambda prime 2 is equal to. Well, it would be lambda 2 times by 1 minus b. Then we've got minus d. We've got plus m. M is 2. And then plus n is also 2. So we'll have plus d minus 2. And the minus d plus d cancels. The 2 minus 2 cancels. So lambda 2 primed is equal to lambda 2. Great. This was just to check that what we did was correct, because we said that the free action is a fixed point of the RG flow. So now we can have a little bit of confidence that the transformation law that we derived is correct. I don't want to keep this result. We're not going to lead it for anything. We know that free action is a fixed point. So let's now move on to some other examples. So the next example that I want to look at, what happens to the mass term? So we've got an integral. So from now on, I'm just going to set d is equal to 4. Everything that I do here for d is 4, you could easily do on your own for general d, okay? So this is an integral d4x. I've got m squared over 2 phi squared, okay? And so what is this coupling going to be? Well, for this coupling, m is equal to 0 and n is equal to 2. There are no derivatives, but there are 2 fields. So the coupling prime, so m prime squared, I could call it lambda naught 2 squared. I'm going to call it m prime squared, will be equal to, we'll have 1 minus b. Then we've got d is 4. So that's minus 4. Then plus m, that's plus naught. And then plus 2 over 2, that cancels. 4 minus 2 is 2. So we land up, and this should be times by m squared, because we've got the lambda mn there. Our coupling is m squared, okay? So m squared. And this would be equal to 1 minus b to the minus 2m squared. Okay. And then if we repeated these steps again, we get another factor of 1 minus b to the minus 2 sitting there. And if we repeat it again, this factor would again appear. So it's good to figure out what's the size of this factor. Well, we know that b is very much less than 1, but we also know it's greater than 0. So that means that 1 minus b is less than 1, and it means 1 over 1 minus b is greater than 1. So in particular, we've got 1 minus b squared, so that's going to be greater than 1. So we learned that m prime squared is greater than m squared. So what we've learned is, under the renormalization group flow, close to the free field fixed point, m squared grows. The coupling grows. Whenever a coupling grows, we refer to that term in the action as a relevant operator. Okay? So the operator in this case would be phi squared in 4 dimensions. So phi squared in d is equal to 4 is a relevant operator. As you keep repeating these steps, the coefficient in front of phi squared will keep growing, and this term will get bigger and bigger and bigger. Great. So you've seen one example of how things change under the RG flow. Let's now do a few more examples.